So today I'm going to explain TornadoVM and our collaboration with Intel to develop one of the parts of this project. But before diving into TornadoVM, I will explain the motivation behind this project and behind this presentation. So heterogeneous hardware are present in almost every computing system today. For example, smartphones and mobile devices contain multi-core CPU plus a GPU. Laptops, for example, contains, apart from the multi-core, it could even contain a couple of GPUs. For example, the integrated GPU that is inside the CPU, and a dedicated GPU, usually for gaming. Even data centers are attaching to today's systems FPGAs. All of this hardware help to increase performance and reduce energy consumption. So they give developers the opportunity to increase a specific type of workloads and decrease energy consumption. And that's great. And we can see more examples even coming up. This is not only one type of devices like GPUs, FPGAs. For example, some companies, startups are developing new hardware for accelerating more efficiently machine learning and deep learning applications. And that's great. We have a lot of hardware, but we need a way to program this hardware efficiently. And in this talk, I'm going to show you how you can do it, an approach of how you can do it from Java and JVM. So that approach is TornadoVM. It's a research project developed at the University of Manchester. So don't worry if you haven't heard about this. I will explain to you the basics and how you can get into it. But in a nutshell, what TornadoVM is a high-performance computing platform for running Java and JVM's applications on heterogeneous hardware, GPUs, FPGAs, and multi-core, ideally with minimal programming effort. I hope I convince you by the end of the talk. So today, I'm going to give you a bit of background about all of these technologies. So don't worry if you haven't heard about OpenCL or CUDA, things like that. So I will explain to you what it is. Then I'm going to give you an overview of the TornadoVM project. I'm going to discuss how TornadoVM generates code for a multiple platform, multiple vendors. And I'm going to focus on one of them. It's a SPV backend. I will explain what it is, don't worry. And the reason behind this backend is because it's brand new. We released this backend a couple of days ago, and that's work in collaboration with Intel. And then I'm going to show you a performance evaluation. And finally, I'm going to show you how TornadoVM is being used by some companies in industry and being piloted by those companies. So hope this is exciting for you, and let's get this. So let's start with the motivation a bit further. We have plenty of hardware. I'll show you at the bottom different examples, GPUs, for example, integrated GPUs, FPGAs, and multi-core. By the way, just for the audience, so the FPGA is like, it doesn't contain any circuits, like a CPU could contain. So the way it's programmed is that you physically wire your algorithms into hardware. So you get rid of the things you don't know in hardware to run the application, and that's why you can get higher speedups. And that's exposed even to programmers. And we can run this with Tornado as well. So, okay, we have the hardware. We have a lot of different hardware, but now how to program those hardware. I'm going to give you a few examples. There are plenty of them. And the more hardware we have, the more tools, the more programming models we have. Here are a few examples. For example, if we take an NVIDIA GPU, you might use, quite likely, something like CUDA. Okay, CUDA is a language developed by NVIDIA, and you can use it for accelerating compute applications on GPUs. If you want to use, for example, FPGAs or integrated GPUs, you might use something like OpenCL, or even to run on GPUs from NVIDIA and AMD. And so on and so forth. But all of these languages, even new standards or new programming models like OneAPI or SQL, they are based on C and C++. But we know, and especially in this conference, that not all programmers are using C or C++. So how do we access this hardware from other languages like Java, R, Ruby, Python, JavaScript, and so on and so forth? Well, the current way is through a call to a native library. Like, for example, if you pick Java, you might use something like a JNI call to a precompiled library that is written in C, C++. But okay, that's one way. I'm not complaining. We're not complaining about this way. It's like in the University of Manchester in research, we believe should be another way of doing this. So what they have in common, these high-level languages, is that they are executed on top of a virtual machine. And that way allow us to write what you want to write, the algorithms and description level of what you want to write, and straight away, don't worry about the details about how to run on the actual hardware. And the virtual machine is the abstraction that can map these two, right? For example, the JVM and OpenJDK, what they can do is that for frequently parts of the program that execute quite a lot, they can compile at runtime those sections of the code into efficient machine code. But that doesn't exist for GPUs, FPGAs, and so on. Right. So if you want to access a heterogeneous hardware from high-level languages, let's pick Java, but a similar situation applies for other languages or even other environments like .NET, for example. If you take Java, you might use something like JDK distribution, OpenJDK, GraalVM, Corretto, etc. Those distributions run on the CPU, for example, an Intel CPU, an ARM CPU, and then the JIT compiler is the component that can efficiently compile hot parts of the program into efficient code, right? Into efficient machine code. But that doesn't exist for the rest. And that's what TornadoVM sits. Okay, so TornadoVM is a plugin to existing JDK, so it needs JDK. And I want to mention that TornadoVM is not a replacement of JDK. It's like a new plugin, okay? It's a new component that allows us to access where the plain JDK cannot access. So TornadoVM is, as I say, it's a plugin to OpenJDK that allows us to dynamically compile at runtime Java code to run on GPUs, FPGAs, integrated GPUs, and so on and so forth. So TornadoVM underneath what it has is a multiple backends, right? We start with the OpenCL backend. That was the first backend that Tornado got. And then we add a new backend for generating PTX with this assembly code of CUDA. And lastly, the last backend we had was for SPV. And it's dispatched through LevelZero. So I know there are many names here. So probably the audience is familiarized with some of them, but don't worry, I will explain each of them, okay? I will make, all of us will make the connection between them. So essentially, we want to study how to access from high-level languages like Java, managed runtime languages, in order to exploit efficiently heterogeneous hardware and increase performance and decrease energy consumption. So we are in exploration phase of many backends and many possibilities, what they can give us and what we can achieve. Right. One thing, the new one that we developed, SPV, I will explain more details in a bit. It can be used for future generations of processors. For example, the upcoming Intel GPU, the dedicated GPU. We don't have now, the hardware isn't available, but we hope we can run there because it runs over SPV and LevelZero stack. Okay, so let's go into the details of TornadoVM, okay? So as I say, it's a plugin for Java that allows Java programmers to run in an automatic manner, as transparent as possible, Java and JVS programs on heterogeneous hardware. And if I have to highlight three key components of Tornado, those components are as follows. So it performs automatic task migration, meaning that Tornado can run for a while on one device, let's say one GPU, and later on migrate execution from one GPU to another, or from one GPU to an FPGA, back and forth. And this is without restarting the application, and fully agnostic to the programmer, okay? The second key component is that it has an optimized JIT compiler per architecture, per vendor. So the code that is generated for running on a GPU is different from running on FPGA or multi-core, right? Again, this is fully agnostic of the programmer. And the third component, well, it's actually that. It's the most important for us, actually, is fully agnostic. So the waste program, the user doesn't know anything about how many GPUs or if I have to program for one GPU, particular GPU, et cetera, et cetera, et cetera. So the TornadoVM project is open source. It's available on GitHub and the GPL v2 with class path exception license. And it can run with multiple JDK vendors, OpenJDK, Graal, Amazon Corretto, Red Hat Mandrel. even Windows JDK build as well. Right, so to show you a bit of more details about the Tornado project, this is the software stack. So there are 4 different components. At the high level, we have an API. And you might think, well, why do we have an API? Well, Tornado doesn't detect parallelization in the program. It exploits parallelization, meaning that Tornado needs a way to identify, okay, which regions are candidates for parallelization. And we get that through the API. And the main concept of the API is a task. Task is the equivalent of a Java method. Okay, and we can create a group of tasks, meaning a group of methods that are going to be executed, compiled and executed on one device, for example, on one GPU, on one FPGA, and so on. Then we have the optimizer. So this is at the user level. The rest is the pure runtime, Tornado runtime, and compiler level. Okay, so then we have an optimizer, and pretty much what the optimizer does is memory optimizations. One of the things that these devices have is they have their own dedicated memory. For example, dedicated GPUs for NVIDIA, they have their own memory. And that means that we have to pre-allocate the regions, the buffers, and arrays on those devices, and then perform data transfer. And data transfers are done through PCI Express, which is usually a bit slow. So if we can optimize data transfers, we can reduce traffic, so we can get overall performance or better performance than we used to have. And that's the goal of the optimizer, essentially. And then we have the whole execution engine. And the execution engine has inside its own bytecode interpreter. So Tornado has its own bytecode representation. I have to mention that for the Java virtual machine, for Java, Tornado is just another Java program. The only thing is that that Java program can compile Java methods to GPUs and FPGAs, but this is still a Java program. And it has its own interpreter, bytecode interpreter. I'm not going to go into the details of interpreting this talk. We have other talks and other publications that we talk about that, so feel free to check our website for more details. But essentially, it's a way of orchestrating the execution. For example, compile this method, run this method, wait for this method to finish, things like that. Those are coded in the interpreter. It's a way of building over runtime, I believe. And then one of the bytecodes is compile, for example, method 1, method 2, method 3. And the compilation is done at runtime. And the compilation, for the compilation, we extend the Graal JIT compiler with more optimization phases and more specific optimization for heterogeneous hardware. And as I said, we have 3 backends, and with that we can execute in a wide set of heterogeneous devices on NVIDIA GPUs, AMD GPUs, Intel GPUs, ARM, Mali GPUs, FPGAs from different vendors, and multi-core systems. Right, so since in this talk I'm talking a lot about OpenCL, CUDA, PTX, and SPV, I'm going to define this very briefly. Okay, this is just a background for the rest of the talk. So I'm pretty sure many of you know this already. It's just to set up the terminology. So OpenCL stands for Open Computing Language, and basically this is a standard developed and maintained by the Kronos Group. Maintained by the Kronos Group, and essentially that was proposed back in 2009, and it's a way, okay, they define a standard way to write compute kernels and run for a wide set of devices, CPUs, GPUs, FPGAs, and so on. So the code is portable because in the same source I can run with in many different places. Right, then the second backend we had was for NVIDIA PTX. And PTX stands for Parallel Thread Execution, and in a sense is the intermediate code that is generated from CUDA. CUDA is the language, let's say. Well, CUDA is many things. So it's the runtime to run the application plus a very small language to express computation. And the translation for those kernels to the actual driver is gone through an assembly code called PTX. It's like an instruction set architecture of CUDA programs. This is developed by NVIDIA, and it only works for NVIDIA GPUs. However, we add it because there are some papers around, and yeah, there's some research around that you can get a bit high performance compared to other approaches, mainly because they know the architecture and they know how to maximize performance. And the last one we add is called SPV. And SPV stands for Standard Portable Intermediate Representation. So it's an intermediate representation still, but it's in binary format. And what is good about this is that this representation, this binary, is compatible with OpenCL. So I can generate SPV binary and run it through an OpenCL runtime. Okay, so allow us distribution of these binaries. That was actually one of the reasons why SPV was created, to avoid licensing issues, to distribute and ship the kernels. So as I say, it's compatible with OpenCL 2.1 onwards. And one of the key things is that it shares IR, it shares the representation with Vulkan, which is for graphics. So that's very appealing for many people. Right, so now I mentioned at the very beginning LevelZero, Intel LevelZero. So where is LevelZero stands here in this set of technologies? Well, LevelZero is a new API that can consume SPV binary. And it's kind of the equivalent API to what you might have for OpenCL, for example. It's a brand new API developed by Intel that allows us to program heterogeneous devices. But that API gives us lower level features than other approaches. And since we started the project with Intel, when the time we start, this was like very recent, very new. So we actually took the approach, okay, let's do it with LevelZero and see what we get. So LevelZero is part of, you might hear about one API from Intel. One API is like a whole software stack, okay, to program heterogeneous devices. It contains many libraries, contains various compilers, it contains an implementation of one of the standards called SQL, and so on. But the good thing about this API, LevelZero, is that it can ship standalone. So we can get it and import it in other projects. And what it contains, well, it's kind of influenced by OpenCL, so it's kind of the same level, but it has all the features that are very appealing for system programming and compilers and compiler programming, like we're doing for TornadoVM. For example, we can have better cache control, we can have memory visibility, we can even tune it. We can, for example, obtain information about power metrics, which is very interesting. We can even control frequency and perform hardware diagnostics, things like that. So I'm not going to dive more into LevelZero. There's documentation around. It's the GitHub repository with source code, as well as the spec. And if you're interested, some time ago, I wrote a blog post about an intro of this technology that you can check. All right, so because we have many backends implementing in Tornado, now what are the advantages and disadvantages of each of them? The pros, the cons and pros of each. Well, OpenCL is the first we wrote as a backend, and it's easier than other approaches because what you generate, or what we generate, is a kernel at the source level. So it goes from Java bytecode to OpenCL C code. So you can read it, you can reason about it. It's easier. Plus, it allows us to figure out the whole software stack, how to go from the Java bytecode down to all optimization phases. I will explain more in detail in a bit, don't worry. And then go down to code generation and execution. And the good thing is that, as I mentioned before, it's portable. So that code can run on other platforms. However, and that's a disadvantage, the performance you can get is not portable, meaning that we have to retune, we have to massage that OpenCL code that we generate in order to increase performance or to get performance even for the platforms. In fact, for example, one of our PhD students, he did a thesis on how to increase performance on FPGAs, basically going from slowdown to very high speed by inserting a lot of new optimizations automatically in the IR level. Right, so then we port to PTX. And as I mentioned before, the main reason for the PTX is because it's highly tuned for the NVIDIA GPUs, and we want to increase performance on those platforms. Also, CUDA, with CUDA, we can get low-level features like unified memory. Well, the OpenCL also has unified memory, but it was released after CUDA. Things like that, okay? And more interaction with the driver. The disadvantage, or the main disadvantage, is that it only works for NVIDIA GPUs. And there are many other devices around in our systems. And other disadvantage, and this also applies for OpenCL, it's like we have low control over the final compilation step, meaning we can generate from Java bytecode to PTX, but then the driver will consume PTX to generate the final binary. And that final compilation step is like a black box for us. So let's say we apply loop unrolling or these kind of optimizations, but we don't know how the final binary looks like. So that level of control in some situations is good to have. And finally, through LevelZero is, remember, it's kind of the equivalent to OpenCL, but lower level. It allows us to have access to low-level features, right? And play with the hardware even more than OpenCL. So we have a higher level of control. As a disadvantage, well, I wouldn't call it a disadvantage, it's by design. It's very low level, it's very verbose, so the learning curve might not be as easy as other approaches. And where SPV stands here? So SPV is how we write the kernel, while other approaches, right, is how you manage the execution. Is how we allocate memory, how we send data, how we run the application, how we get the data back, and so on. But the functions that can run through SPV binary. So SPV can be consumed by these frameworks. I hope this is clear, okay? So if you want more information, please check the documentation for each of them. So you might think, okay, Juan, but why all these backends? It seems like, for example, OpenCL is good enough, right? You can get a lot of devices. So why are you mixing in your group? Why are you investigating different approaches? Well, this is a bit philosophical question. So you might think, well, if this is good, right, a good approach, why other mainstream environments like OpenJDK or .NET don't have this already, right? This seems like a good thing to have. And in fact, I'm going to show you and justify the huge speedups you can get with this approach. However, how to get there is not a unique solution, right? So if you download JDK in the distribution, and it's like kind of the standard to go for assembly code or x86 code or ARM assembly code and run it from there, right? And generate code for that platform with that technology. But on heterogeneous hardware, there is no clear path. There is not a unique way or like the panacea way, right? So that's why we're investigating different options. And not only to investigating options, not only for the end user, the speed that you can get or the energy you can save, but also to how to maintain all these compilers over time. So our goal is to have an existing code in Java, for example, that can run on many platforms and new platforms over the future years, right? And how we adapt those changes, well, we need to study how those changes are migrated. I mean, how we can quickly adapt to new hardware, new environments, new programming models, and so on and so forth. So that's what I'm doing. So we do research on this area. We give this research through publications and talks to the community, and we receive feedback back from the community, and we are in this cycle. So what I would like is to involve our listeners in this process, right? You can get involved in this process. You can talk to us on GitHub, open issues, discussions, and so on. Because we want to shape the next generation of computing systems and programming language with this with heterogeneous hardware. Things are not clear; they don't have clear answers. For example, which technology is the best, or which are the best in which scenario, okay? Or if the what features can be exposed to managed programming languages from low level, right? Because as I said at the very beginning, keep in mind that many of these models are based on C, C++, but we want access from others, right? Native access from other programming languages. Okay, so enough talking about technologies. Let's dive a bit more detail into each of these backends, right? How TornadoVM compiles and runs a managed execution from Java. So let's get into that. So here I show you an example. It's a piece of Java code. I will show you a complete example later on, so don't worry about the specific details. In a sense, what we want to do is to have an application that is close to what you have a sequential application, right? An existing Java application. And here I show you the StackSpy. It's a method, Java method. You pass the parameters, and there's a for loop. And in the for loop is the computation for solving StackSpy. Basically, like a vector addition, and you multiply first value by a scalar, right? It's typical computation for linear algebra. Very simple. So that's what the user or the developer will write. That's the developer or programmer's view. There is one annotation called add parallel. This is exposed, so Tornado will expose that to the user. I will get into the details later. But in a sense, the developer writes an application that is close to sequential. One of the APIs that Tornado has, have other ways. And then it will compile the code as usual with Java-C compiler. And now you enter in the Tornado runtime. So from the Tornado runtime, the first thing we do is to build the intermediate representation that corresponds to the methods you want to accelerate. In this case, it's StackSpy. And for that, we use Graal. So we extend the Graal JIT compiler to compile for heterogeneous hardware. From the Graal IR as it is, we expand with more information. For example, we add information where the parallelization is located, the parallel loops are located. We add information about memory regions. GPUs have memory different programmable regions like local memory, share memory, constant memory, private memory, and so on. Those information is in the common IR. And then from that common IR, Tornado will pick one of the backends. The user can also pick one, but usually Tornado will choose for you. And then we specialize the IR per vendor, per architecture, per backend. Okay. In this case, there are only 3, but imagine there are many different of IR, as many as devices we have underneath. Then we optimize the code in that intermediate representation. Don't worry if you don't read the details, it's on purpose, okay? I'm not gonna go into the details of the IR in this talk. And then from when the IR is optimized, then we generate corresponding code. So in the case of CUDA, we generate the PTX assembly code. In the case of OpenCL, we reconstruct the OpenCL C code. And in the case of SPV, we generate SPV binary. And with that, we ship this, we send this to the actual driver. The driver we have underneath could be CUDA, OpenCL, or LevelZero driver, and dispatch the application. Tornado will handle memory, will handle synchronization, will handle execution, Tornado will know in a sense how many threads to run, how many blocks of threads to run, and so on and so forth. Right, so let me focus on one of those. One thing I want to mention is that TornadoVM, so if you choose the SPV backend, as I mentioned, as I put here, ideally, or the solution is that this SPV can be used also for OpenCL, can be consumed by OpenCL. The reason I'm putting this is that for now we focus on LevelZero, but LevelZero only works for now on Intel HD graphics, but it's an open library, and the spec is open. So we hope in the future more vendors and devices are available in the future. Same as OpenCL, right? Okay, so in more detail, let me show you how this PV looks like. I show you here the same application, StackSpy. Then remember, we build the intermediate representation. It's in the graph form, and then we optimize in a graph. Essentially, from this point, it's a graph problem. We remove nodes, we include nodes, we expand nodes, and so on and so forth. And those nodes has meaning. For example, if we see a loop, but the loop is parallel, we remove the loop and put parallel loop annotation in there that is able to generate the code properly, right? When we have to generate code. We optimize this, we have a lot of optimizations, and that's another key, because the optimization for heterogeneous hardware, GPUs and FPGAs, are fully integrated in the Java pipeline. In this case, in the Graal-JIT pipeline compilation. So we can combine well-known and existing optimizations like loop unrolling, partial escape analysis, concept propagation, and these things. Maybe we have to tune some of those. For example, we have a tune for the loop unroller on FPGAs, which can give us better performance, and we don't use the one provided by Graal. But those are details to increase performance. But in a sense, we can combine existing compilation phases from Java and the Graal with our own compilation phases. And that's one key difference with other approaches in the same arena. For example, Aparapi or other approaches, they have other way of generating code. Right, so from there, we generate, in this case, I show you a piece of SPV code. So I don't pretend to understand SPV code. It's just an example, okay? So SPV is in binary format, but you can disassemble the binary and see how it looks like. And from there, we install the code in a code cache. So if the same expression or you run the same method over and over again, we don't have to recompile. We just run it from the code cache. And running on a GPU or whatever device is available on the system. Right, with that, I want to jump to more fun stuff. So let's go the Mandelbrot fractal. So I think many people are familiarized with this type of image. It's a fractal, it's called Mandelbrot. All the examples are available on GitHub in this URL, so feel free to check the website, the GitHub repository along with this explanation. So this is a class, it's called Mandelbrot, Java class, and it has two methods. First method is called Mandelbrot fractal, and that's the method we want to offload to the device. In this case, we're going to use an integrated GPU, okay, an Intel integrated GPU. As you see here, there is no information about where to run. Okay, there is no GPU information, there is nothing around. It's just Java, and that's one of the key points. So let's focus on the first method, fractal, Mandelbrot fractal. We have an input, the size of the image, and the output image we want. Okay, in this case, it's in a short array. And this has two loops. So what we want to compute is the value for each pixel, okay? And each pixel can be represented in a 2D space, so x-axis and y-axis. So what we're going to do is traverse in x-axis and y-axis and compute the value of each pixel. I show you here for simplification just the first two loops, and the rest is the actual computation for the fractal. So for the actual computation, please go to GitHub and check the code in there. But I want to mention the two loops. Why? Because, as I mentioned, each pixel can be computed independently of any other pixel in the image. So ideally, these can be computed fully in parallel. And we can do in two level of parallelization, 2D. So that's why the code is annotated. This is annotation exposed by Tornado to the user, and it's called add parallel. Okay, so the user thinks these two loops are parallelizable, and it's a weird expression. The user thinks these two loops are parallelizable. So the reason I'm saying this is that Tornado will check that these two loops are actually parallelizable. So this is a hint. So Tornado will look for those hints, and then we'll double check. Do I have dependencies between iterations? Is it safe to parallelize? And if that's the case, it goes for it. Otherwise, it baits loud and execute the sequential code, because running the parallel code is invalid. It's not semantically correct. Right, that's one thing. And the second thing is we need to identify which methods we want to compile. And we do that through the task schedule API. And here is an example. So we build a task schedule. It's an object that Tornado exposes. We give it a name. In this case, it's S0 as a task schedule. And then we can give names to each task. We can have as many tasks as we want, right? In this case, there is only one. And the task has a name, and then it's a reference to an existing Java method. So it's a class dot the method to be compiled, right? And the rest is the normal parameter for this call. And then we call stream out. Quite likely the the memory between these devices are not shared. So Tornado offers you a way to synchronize the data, which I'm expecting the result in this variable. So once you finish the execution, okay, give me the result in this variable. So I can see actually what's happening is that it's going to copy from the device heap to the Java heap. And then you can continue execution as usual as any other Java program. And then with the task schedule, you call execute. And once you call execute is where the JIT compilation starts and the execution starts. So this is the kind of the task definition, okay? And then it's the execution. Okay, so let's do that. I have the demo prepared. Hope you can see the screen. Let me increase the font. So first of all, what I'm gonna do is to inspect the devices that are available. And I can do that through a command in Tornado. I run tornado -- devices, and let's see what we get. Oh, interesting. So Tornado tells us that on this machine, I'm running on my laptop here now. I have 3 drivers. You can imagine like the driver word as a backend, okay? 3 backends. First one is SPV backend, interesting. And then I have a list of devices that are executed under that backend. So in this case, I only have 1 device for this backend. And it's going through the LevelZero dispatcher, and the device is the Intel HD graphics. It's the GPU that is inside the CPU. That's great. Then the second backend is OpenCL, and in this backend I have 3 devices. I have a big one, NVIDIA GeForce 2060 is a good GPU. Then I have an Intel HD graphics. This is the same that the SPV give me, but the dispatcher is different. So this will go through SPV binary, this will go through OpenCL, but the device is the same. And I have also an Intel multi-core system. So I can run OpenCL through an Intel multi-core, right? So you can actually use the multi-core. And in fact, as a key message as well, don't underestimate the power of OpenCL with multi-cores. Is usually very good. And the last backend we have is a PTX. So we generate PTX, and obviously PTX is proprietary by NVIDIA. We run the PTX code on the NVIDIA 2060. So let's run that. All the instructions are on GitHub in the same URL I sent you. So what I'm gonna do is to run a multi-thread application. I hope you can see the screen. So I run in Tornado, I'm just passing what it is, and I'm running the Mandelbrot computation, and I pass a flag. The documentation of this is in the example. Basically, I'm running with parallel streams. So I know I'm running with Tornado, but I'm not using Tornado at all. I'm running with usual streams from Java 8. It's just to get a baseline, some numbers. And I run it multiple times. So this is just to show you a quick demo, okay? Don't take these numbers as a whole, benchmark. So if I run it, I get, okay, around 300 milliseconds, 299 milliseconds, yeah, 300 milliseconds around. And I'm running with 16 cores. So this machine has 16 cores in it, okay? So now I'm gonna enable Tornado and see what we get. If I enable Tornado, oh, it already finished. So instead of 300 milliseconds, it takes 59 milliseconds. So we get a bit of speed over the 16 cores that we got from parallel stream API. And you can say, well, Juan, this is very abstract. I don't see anything. Maybe it's not running there. Okay, we have a flag to tell Tornado, give me the information where you are running this code. And it's called thread info. Let's see what we get. So here, interesting. So it's running with SPV backend on an Intel HD graphics. That's great. In fact, we can inspect the code that is generated. So if we run with the debug flag, let me show you here. If we run with the debug flag, the first time we run it, it will spit out the file with the SPV binary, and we can disassemble that binary. We can do SPV disassembly. This is a tool from Kronos, so it's a standard tool. No, there's no modifications in there. And that's the SPV we generate, okay? I'm not gonna go over it. It's just to show you an example, right? So if I go to the header of this file, what it's giving me is that it compiles a code, a method called Mandelbrot fractal, and those are the parameters, and this is the code, all variables we use, and so on and so forth, right? So that's great. Just for reference, I'm going to show you how to change the device. So remember that SPV took around 59 milliseconds, and we can change the device through a command of this. So remember that I gave names in the source code, and I can change the name, and I can change the device with that name in it. And in my case, the OpenCL with Intel graphics is the reference 1.1, and I run it with debug info and so on, and I see that the OpenCL driver with this application, with this image, the same input size, takes 55 milliseconds. It's a bit slower than it used to have, right? So it's actually 10% slower. So the SPV can give us a bit of extra performance in this case. Right, so let's go back to the presentation. So when I run these benchmarks and I compare against Java sequential, I got this. So if you run the parallel stream, you can get 12 times faster on 60-core machine, not bad. And if I run it with OpenCL, I can get 46 times faster. And if I run with PV, 50 times faster. And in fact, if I compare against parallel stream, it's like 4 times faster. Right, so I run this application, but okay, I show you the code, I show you a bit of the metrics, but what's happening underneath? Why this is a speed? Why we get this speed up? We can actually have profiling information in it. And we do that through a command, an option in Tornado. It's called enable profiler. And we will get back a string in a JSON format. And it's like that. So remember that our way we code it, we give names to the tasks, S0, T0, and we will have sections corresponding with those names. So this is the global metrics, meaning the global timers for all tasks that belong to the same graph, and then each task separately. In this case, we only have one. It's the Mandelbrot fractal. And here appears the method that was compiled. And from there, we can get a lot of information. For example, we can get the total time of the execution in nanoseconds. These all times are in nanoseconds. And are end-to-end, meaning for the whole JIT compilation, data transfer, so on and so forth. We can get also the time that was with the Graal compilation. So from Java bytecode, all the optimization, and code generation. Or we can get, for example, the time when we ship this code to the driver, the time to compile from the driver, from the actual representation to the actual binary. And if you want to access, for example, the time for the kernel, so this is the time for, before I show you the time for the overall application, right? But now we want just the kernel, the GPU kernel or the FPGA kernel. I can access that, and that's stored here. And we have the timer for each separate task. We can also access the time for transfer data, the copy in data, copy out the data from the device, and so on. So what do we get from this? Well, if your bottleneck is data transfer, the device you're using is not a good candidate, right? Ideally, what we want to use is what we want to see is the bottleneck in the kernel time. If we want to use a heavy compute device, for example, a GPU, big GPU, an FPGA, and so on. However, having said that, we have other strategies that we can include in Tornado. They're not done yet. We are doing research on that area, for example, to share memory and to do pin memory. And with that, it kind of alleviates the issue of, okay, maybe the kernel is not the majority, but we can do very fast data transfers, and you can still get speed ups, right? That's the key message, right? So if you don't get speed ups, look at the kernel, and that's why you're gonna see. So usually the kernel is very small portion when you don't get speed ups, and the majority is spending in traffic, which is something in our issue as well. I mean, we want to improve that part as well. Right. So just a few words about more performance with this. So I run, instead of just the Mandelbrot fractal, with other applications like DFT, Mandelbrot Embody, and we got really, really high speed ups. And the key message here is, don't underestimate the GPU that you have in your system, the CPU. This is I execute this on the integrated graphics with SPV backend, the new one. And you can get, for example, DFT application 300x performance compared to Java sequencer. Okay. If I compare with other backends, this becomes really more interesting. So here the x-axis shows the application, the y-axis shows speed up against Java sequencer. So the higher, the better. And I show different implementations: SPV, OpenCL with different devices, and the PTX. And the SPV, for example, is very competitive sometimes. In other cases, it's slower. In other cases, it's faster. For example, DFT is twice as fast, even faster than the dedicated GPU, which is quite interesting. This is because we use a lot of intrinsics underneath. But for other cases, OpenCL and PTX and SPV, sorry, are on par. And for other cases, SPV is just not there. There are many things this is what we're analyzing. There are many things in place. It's not just the code gen, it's how you dispatch threads, but this is for other discussion. Right, so what about running other programming languages? So Tornado actually can be used to run from other programming languages. And we can do this through Truffle. We have demos, live demos, if you are interested. For example, QCon London 2020, we show a demo running Node.js application in the web browser on the GPU. So in a sense, we express the computation, instead of expressing computation in CUDA OpenCL, we express the computation in Java, and that Java code can be invoked from higher level programming languages like Python, Ruby, R, etc. In fact, here I show an example. You can run Python program. It represents the matrix multiply. The Python code has a call to Java code that computes matrix multiply, and if you print with debug info, you will see running on the accelerator, which is quite interesting. Please check our website. We have other cases and other programming models, other programming languages with examples and so on. So just to finalize, just 2 more minutes to finalize, TornadoVM can be used for more than fractal computation and things like that. In fact, we can run very different domains. For example, in natural language processing, IoT, digital signal processing, physics simulation, computer vision, fintech applications, or even machine learning and deep learning. Many of these numbers are taken from collaborations with industry. So you can see, for example, in machine learning, we get a 14x performance, or natural language processing 30x performance, or for more compute, heavy compute, performance is even higher with big GPUs, obviously, even 1000x performance compared to Java. So for details about all of these numbers, please refer to our publications, academic publications, and our blogs that explains in detail all of these use cases. So as I say, TornadoVM is open source. It's under the GPL v2 license with class pass exception, so you can use it and you can combine with your own projects. And it's also available in Docker. So we have Docker images that you can just pull and run, give a try. Tornado. For now, all the Docker images we have is for OpenCL, but it's easy to build a new one for the backend. And there is a team underneath. This is not created with just one person. The team is mainly composed of PhD students, master students, and bachelor students, and some of members of staff. And we are looking for feedback. As I mentioned earlier, I think that's the time that we have built expertise in many different programming models and domains regarding heterogeneous computing systems. And we want to talk with industry, and we want to talk with academia and get feedback and collaborate. And we believe in this technology to build better computing systems that are aware of heterogeneity and energy efficiency. So with that, I conclude my presentation. So just key points to remember. I hope I convince you that heterogeneous hardware are here and are here to stay. Practically in almost every computing system, you're going to find a combination of different types of processors. So the issue is how to get access to those hardware. I show you an approach how to get that from Java. It's called TornadoVM. And I show you different backends that we generate, different technologies that we use underneath. And we are studying these technologies separately to increase performance and decrease energy consumption. I hope I convince you that we can get very high speed ups usually 100x speedups. And with that, I conclude my presentation. So if you have made until this point, thank you very much for your attention. And I'm happy to take questions in the Q&A session. So thank you very much.
Thank you. Thank you, Juan. As you said, I also invite participants to join the Q&A rooms to ask questions to Juan about TornadoVM or maybe any other questions you might have. So you can find the links to Q&A rooms in the discussion section of the menu. So please continue. And Juan, we are very, very thankful for your talk. And so thank you for supporting our events online this year. Hopefully next year it can be done offline and you can come to Kiev. So thank you.
Thank you very much. Thank you, all of you. Thank you.
Have a great day.